Introduction. Amines are organic compounds and functional groups containing nitrogen atom with a lone pair of electrons. They are derivatives of ammonia, where one or more hydrogen atoms are replaced by alkyl groups or aryl groups. This seemingly simple substitution leads to a diverse range of compounds with significant properties and application across various fields. Classification of amines. Amines can be classified based on the number of alkyl or aryl groups attached to the nitrogen atom and the nature of carbon group attached. Classification based on substitution amines are categorized according to the number of hydrogen atoms replaced in ammonia. So we have primary amines, which is one hydrogen atom in ammonia are replaced by an alkyl group or aryl group. For example, methylamine. Let's go to secondary amines, which is two hydrogen atoms in ammonia are replaced by alkyl or aryl group. One of the examples of that is dimethylamine. Tertiary amines. All three hydrogen atoms in ammonia are replaced by alkyl or aryl groups. One of the examples of that is trimethylamines. Structures of amines. Now that we have classified amines, let's look at their structural properties, which significantly affects their chemical behavior and reactivity. Hybridization and geometry. The nitrogen atoms in amine is sp3 hybridized, forming a trigonal pyramidal shape due to the presence of lone pair of electrons. Bond angle. The bond angle in amines is slightly less than 109.5 degrees, or which is the tetrahedral, due to lone pair repulsion, typically around 107 degrees. Lone pair effect. The lone pair on nitrogen influences the reactivity and basicity of amines, making them capable of forming hydrogen bonds.
Let's talk about the properties of amines. The properties of amines are significantly influenced by their structure and the presence of lone pair of electron on the nitrogen atom. First is the basicity. Amines are weak bases due to the lone pair of electrons on the nitrogen atom, which can accept a proton to form an ammonium ion. The basicity of amines depends on the nature of the alkyl or aryl group attached to the nitrogen atom. Generally, aliphatic amines are more basic than aromatic amines. The second property is the solubility. Lower molecular weight amines are soluble in water due to the hydrogen bonding with water molecules. However, solubility decreases with increasing molecular weight. The third property is the boiling point. Amines have higher boiling points than comparable hydrocarbons due to the hydrogen bonding between amine molecules. However, their boiling points are lower than those of alcohols with similar molecular weight because NH bond is less polar than OH bond. The last property of amines is odor. One of the most distinctive properties of amine is having their pungent odor. This odor is particularly pronounced in the lower molecular weight amines, frequently described as having a fishy or ammonium-like smell. However, as the size and complexity of the amine molecule increase, their odor tends to be less noticeable.
Next, let's proceed to preparation. Amines can be prepared through various methods including: first is the alkylation of ammonia, wherein ammonia reacts with alkyl halides to form primary, secondary, and tertiary amines. Second is the reduction of nitro compounds. Nitro compounds can be reduced to primary amines using reducing agents such as hydrogen gas with a metal catalyst. Third is the reduction of nitriles. Nitriles can be reduced to primary amines using reducing agents such as lithium, aluminum hydride. And the last one is Gabriel synthesis, and this method allows the synthesis of primary amines from alkyl halides using potassium phthalamides.
For this part, I am going to discuss the applications of amines. First, for pharmaceuticals, many drugs contain amine functional group, including many neurotransmitters, antibiotics, and antihistamines. For dyes, aromatic amines are used in the synthesis of various dyes. For polymers, amines are used in the synthesis of polyamides. Example given, nylon and other polymers. For agriculture, some amines are used as herbicides and pesticides. And lastly, for the rubber industry, amines are used as accelerators in the vulcanization of rubber. In conclusion, amines are a crucial class of organic compounds with diverse structures, properties, and applications. Their basicity, solubility, and reactivity make them essential building blocks in organic synthesis and crucial components in various industries. Further research continues to uncover new applications and expand our understanding of these versatile molecules.
Today, let's dive deep into the fascinating world of amines. What are amines? Amines are organic compounds derived from ammonia. Using butylamine as our example, we'll explore how amines react with water, acids, alkyl chlorides, halogenoalkanes, and metal ions. Let's break these reactions step by step, focusing on why and how they react. Let's start with the simplest reaction. Amines reacting with water. Amines are weak bases, and this all comes down to the lone pair of electrons on the nitrogen atom. Imagine nitrogen and butylamine as a tiny clock. You grab a hydrogen ion from water. When butylamine meets water, the nitrogen steals a hydrogen ion from a water molecule. And what's left behind? A hydroxide ion. This creates two things: a positively charged butylammonium ion, and those left over hydroxide ions make the solution alkaline. So, when amines dissolve in water, they create slightly basic solutions. This is why amines like butylamine smell fishy and fails the burn. Classic traits of weak bases.
Next, let's make an amines with an acid. Think of this as a classic acid-base reaction. Butylamines nitrogen, with its eager lone pair, snatches a proton from the acid, hydrochloric acid. The nitrogen becomes butyl ammonium, and the acid's conjugate base sticks around. If you evaporate the water, you're left with butyl ammonium chloride, a salt. This is why amines are used in pharmaceuticals, because they form salts, they are stable salts that dissolve easily in the body.
Now let's round up the complexity with acid chloride. Acid chlorides are reactive because of their polar carbon-chlorine bond. The nitrogen in butylamine acts as a nucleophile. It attacks the positively charged carbon in acyl chloride. This triggers a nucleophilic addition-elimination reaction. Butylamine's nitrogen bonds to the acid chloride's carbon. A hydrogen chloride molecule gets kicked out. The result, N-butyl ethanamide, a secondary amine. This reaction is crucial for making polymers like nylon or painkillers like paracetamol.
Ever wondered how to build nuclear amines? Use a step-by-step process. The nitrogen in butylamine attacks the partially positive carbon in chloroethane. The chlorine atom is replaced, forming a new carbon nitrogen. This creates a secondary amine, two carbon groups attached to nitrogen. But wait, there's more. The secondary amine can react
When you add methylamine to a copper solution, a light blue precipitate forms first. This is the copper hydroxide. Adding excess methylamine dissolves the precipitate. Because the amine acts as a ligand, bonding to the copper ion to create a deep blue complex ion. This color change is a hallmark of transition metal chemistry, showing how amines can stabilize metal ions in solution.
In conclusion, amines are versatile bases due to nitrogen's lone pair. They form salts with acid, amines with acid chlorides, and bigger amines with halogenoalkanes. The reaction with metals highlight their role in coordination chemistry. Whether you're synthesizing drugs or studying biochemical pathways, understanding amines reaction is superpower. Stay curious and keep experimenting.
Thanks for joining into this deep dive into amines chemistry. For more organic reaction, check the links below. Until next time, keep those molecules moving.
Thanks for watching!